about chapter 9. You know, there's crashing we talked about. We had a homework problem on it. What we didn't go over enough maybe in this class, I wanted to kind of steer your study on chapter 9 is the unknown or estimated service times to do an activity, and then we were able to get a variance for the project, and then we were able to convert that to standard deviation for the project, and that way we could find the probability of any amount of time or less, or amount of time or more, based on the expected project time and that project variance or standard deviation. Does that sound familiar? So that probability and how you got it, I put an example of, actually from the other class. I think I posted it under chapter 9's PowerPoint. So look in that area for an example I posted that you might want to print and have with you. And then there, obviously, the beginning of chapter 9 was if we're given activity times that are known, not uncertainty where we get 3 of them, where they're known. And we learned how to do the forward and backwards pass. We get the expected amount of time. There's no probabilities in that one because the activity times are known. They're not estimated with a range. It's only with the unknown or uncertain estimated times where you have the fastest it could take, the longest it could take, and the most likely. Those are the ones where we could get probabilities for. So, chapter 11, we talked about there's 4 waiting line systems, theories, that we're going to study for this class that could be on your quiz. They're all Poisson arrival. So at least you don't have to sit there and figure out what kind of arrival it is. Poisson. Even though there are other kinds of arrivals, most of them are Poisson, follow Poisson type probability. But there's, as far as service, there was exponential service single channel, exponential service multi-channel, arbitrary service single channel today, constant service single channel. Those are the 4. And we were talking in my office just a little bit ago, what would be the first step to attack a waiting line problem, or second step? It's interchangeable. Either the first or second step, though, is to figure out what kind of a problem are you reading. Is it exponential service, single, multi-channel, or is it arbitrary or constant? And I gave you some specific things to look for so you could identify which one it is. And for arbitrary, I said look for the, that's right, standard deviation or variance or something like that. Only arbitrary will be giving you the standard deviation or variance of the service. Constant, I said to look for where the service is being provided for the exact same amount of time for every person that has the service, every unit that has service done. And usually, not always, but usually there's probably not a human involved that takes a lot of variance out of the service thing. It's probably a machine or a robot or a vending machine or something that will do the same amount of time every time. That's constant. And then you should have these page numbers down. I don't have them memorized. But arbitrary and constant use the exact same formulas except for L sub Q, the average number weighting, I think is what that is. Constants is on the next page. You substitute L sub Q if you have a constant problem, but you're using all the arbitrary formulas other than that. So these, you should have the same page number down, plus the extra page for this one to make the swap. Exponential multi-service, you got like 3 pages. What is it, 5, 17, 18, 19, I can't remember, but right around there. And that P sub O, which is your probabilities of no customers in this to be served, or no units in the system, that one for multi-channel, you're really much better off to use the table on 519. Take arrival rate divided by service rate, and then go to that table. Is it 2 channels, 3 channels, 4 channels, and get your P sub O, your probability of no units in the system. Then calculate your L sub Q, because you need that P sub O. Then get your L. In case there's an economic analysis question, you're going to need that L. Multi-channel's got the most work, I think, as far as, because it's, you got that difference. How do you recognize it? It will be the only problem that talks about more than one service channel at a time. Don't get confused where we're thinking about 2 different people or 3 different people. Who's going to work one service channel? That's not multi-channel. It's where you have to make a decision whether to be opening 2 tellers or 2 theater ticket takers, or 3 or 4. All of them are more than one working at the same time. That's multi-channel, and you know to go to those formulas, 5, 17, 18, 19. If it's not one of these 3, arbitrary, constant, or multi-channel, process of elimination leads you then to exponential single channel. That's how I do it. You know, look, if there's some other way you want to recognize exponential single channel service, please write it down and share it with us, because I usually use process of elimination. That's kind of the hardest one to recognize. Now that we kind of did a semi-review, I want to make sure we review the economic analysis and make sure you know exactly what's involved in that calculation. In economic analysis, there's 4 numbers involved. Here we go. Here's the 4 numbers you need. You need the cost per channel for 1 channel. Do not multiply it times 2 or 3 or 4, however multi-channels the question may say, if it is a multi-channel. So it's the cost per channel. That would be like the employee's cost for the wage and the benefits and everything per maybe hour. You multiply that times the number of channels. For the 3 of these, the number of channels is 1. You're multiplying times 1. But the multi-channel, it could be a 2 or 3, 4, 5. The other part of the economic analysis formula is the weighting cost times L. I hope you got that in your notes, because this economic analysis could be used for any one of the 4, whichever the service may be, exponential or arbitrary or constant or multi-channel. And L represents the same thing, but they're not the same formulas. So that's why you don't calculate L until you know what kind of problem you're looking at, so you go to the right L formula. They all represent the average number in the system, but there's different formulas based on whether it's multi-channel or single channel. So, or if it has arbitrary or not, or constant. They have different, to get to L, they have different L sub Qs. So that's why you've got to make sure you're using rates. You got to make sure you recognize which kind of problem you're reading as far as service. You know, then if it's an economic analysis, the hardest part's going to be to calculate the L if it's not given. Almost always the cost per channel for an employee doing the job and the weighting cost will always be given in this class. In real life, the weighting cost is the hardest part of this whole thing. All right? So here's an example. This was the trader, the stock exchange trader on the New York Stock Exchange who was getting calls coming in, and the calls were coming in at 20 per hour, but then they did some advertising which raised the amount of calls coming in. They expected to increase by 50%, so now the calls are coming in at 30 an hour. And so they're deciding to take on a second trader to handle the calls and do the service. The advertisement went so well, I believe this says, that they doubled the amount of calls coming in. So now they're 40 per hour. And they're trying to figure out whether they should bring on a 3rd person to take out the calls and handle the service, or leave it at 2. So here's where economic analysis comes in. And in real life, the economic analysis is part of the decision and really kind of the most important part. But the second most important part is that probability of a customer having to wait. In real life, I've met a lot of businesses who focus on that probability a customer has to wait, because businesses want to be the best customer service they can provide as long as it doesn't cost a lot of money. So that's why you got to have that cost also. So in this case, they're saying, should we have 2 traders or 4 traders, or 3 traders, excuse me. The cost per trader, no matter how many we have, is going to average about $20 per hour. We're subcontracting them. We don't have to pay benefits, let's say. So $20 per hour. The waiting cost is 50 cents per minute. Now, that $20 per hour needs to be multiplied times 2 in one calculation, but it needs to be multiplied times 3 in the other economic analysis calculation. Because it's the same cost, 2 channels or 3 channels is what we're evaluating. The waiting cost is given to us in minutes. We can't use 50 cents. The cost per channels in hours, our arrivals at 40 is per hour, our service is at for one channel is every 2 minutes, so we converted that to a rate. 60 minutes divided by 2 minutes is 30 per hour. And if we take on a second trader and third trader, they're all going to be at about every 2 minutes, so that's 30 per hour. I want to refresh your memory. Anytime the arrivals or service are given to you in time, oh, they arrive every 3 minutes. The service takes about 5 minutes on average. You have to convert it to rate. For all 4 of these, to do these formulas, it has to be not how much time. When you read it, is it telling me how much time? If so, you got to convert it to how many during a period of time. A lot of these are per hour or per day. Some are per minute. Whatever the unit of time is how many is what you have to use in all 4 of these formulas from those pages I gave you. Now, I would rely on those 4 pages, the pages I gave you for the formulas, and recognize that one symbol is the arrival rate and the other symbol is the service rate. Just figure out the symbols and plug in them 2 numbers. That's all you need is those 2 numbers. In this case, even though we're considering 2 or 3 traders, we use the service rate per 1 trader when we're calculating our L. And the service rate per trader was every 2 minutes divided into 60. They could help 30 calls. They could take on 30 calls an hour. Customers are doubled, so they're coming at 40 per hour. So we're going to put 40 per hour, 30 per hour is the service. Number of channels, we're going to put it 2. Cost per channel, $20. What about the waiting cost? Everything else is in hours, but the waiting cost is 50 cents a minute. What do I convert that? We got to take the waiting cost and change it to per hour because our arrivals per hour, our service per hour, and the cost per channel per hour. You've got to have the waiting cost per hour. 50 cents a minute times 60 minutes, our waiting cost is $30. So $30 times L, $20 times K, which is a 2, and then we do it again as a 3. They have 2 different L's, but the waiting cost is $30 for both of the formulas. Now all we need is the 2 different L's. We go and we go in and we calculate the L's, we set it all up, $20 per channel times the number of channels, $30 per hour waiting times whatever L is for 2 channels, whatever L is for 3 channels, and where's the calculation? What is it here? We don't do this formula for multi-channel. Instead, we take 40, they're coming in at 40 an hour, divided by the service per channel of 30 per hour, 1 point something. We look up 1 point something on our table. We find P sub O to be, where's the, 0.2. All right? Does that whole thing come to 105? Oh, and that's my me saying use the text. Do not do this. Go to page, it's a different page each edition, but it's 519, I think. And if you take 40 divided by 30, and you go underneath, how many channels is this one calculating for? 2 channels? 2 channels. See if it says 0.2 on that chart, on that table. What's 40 divided by 30? What's 1 point what? 4 divided by 3, 1 point what? 25? 1.13? Anybody here? 1.3. 1.3. Look up 1.3 on page 519. Go underneath the 2 and tell me if it's 0.2. Is it 0.2 on that table? What's going on? Why is anybody talking? Do I have to edit this out? Can't believe it. Is anybody here? If you're not understanding this, you've got to get ready to ask questions. And if you can't remember your question, write it down. So I want to make sure you understand this. You have a quiz this Friday, right?
Monday.
I'll be here. What's going on? All right. 1.33 is not on the charts. Right between 1.2 and 1.4, I go over to 2 channels. Somewhere between 0.25 and 1.765, so you weren't answering because it's not there. Right between those 2 numbers would be 0.2, we'll say. And that's what it says on the PowerPoint. If we could do the whole formula, we would get 0.2. Estimated. If you use either of those numbers, I'll be happy. I don't care if you round up or down. I'm so happy you used the number off the chart, you know, and I didn't pick this. This is multi-channel. To get to L, we've got to do L sub Q, which needed that 0.2. L sub Q uses that 0.2 right here. Arrival, 40 divided by 30. There's 40 times 30. K minus 1, there's two channels we're doing right now. 2 minus 1 is 1. Factorial, 1 factorial is 1. Just to refresh those who weren't here last lecture, factorial is the number being factorial times every number down to 1. 5 factorial, 5 times 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. Just to refresh your memory. Go all the way through, do the math on this, we get 16/15, 1 point, whatever this is. To get to L, we take what we just calculated, add it to the arrival divided by service, which is 40 divided by 30, and we get 2.4. Now we have L for two channels. The economic analysis can be done. 2 channels times the cost per channel of $20. 2.4 is the average number in the system with 2 channels times the waiting cost. $112 an hour if we have just Joe and that second person we hired taking these calls, even though they're coming in fast. And in real life, we want to know the probability of call after wait, because they'll call another brokerage to get their sale done. Now we're going to do 3 channels. We got to get that piece of O again. Now we're taking 40 by 30. Again, it's in between 2 numbers. Again, in between 2 numbers, which is right there between, I forgot already, 1.2 and 1.4. We're going across the 3 this time, which is right here. So our piece of O is somewhere between 24-ish and 29%. We'll use like 26.26 maybe. Let's see what the PowerPoint says. 0.2542. Close. Right? See how to get it off there instead of doing this long calculation? 0.2542. This is 3 channel now, so we have a slightly different hour. That's what we're going through. Plugging that in to get our L sub Q. Average number of waiting. There's where we would use what we just calculated. L sub Q, if we plug all this time, is 3 minus 1 factorial. 2 times 1 is 2. Do all this, we get 0.1446. To get to L, we got to use that, the average number in the system. You got to use the average number waiting, add to it the arrival divided by service, 40 divided by 30, 1.478. Now we can do economic analysis for 3 channels compared to 2 channels. 20 per channel, this time times 3 instead of 2. $30 waiting cost, but this time it's multiplied by 1.478. If we have 3 taking calls, our cost per hour, because we're reducing the waiting cost, even though we're spending $20 more with a 3rd employee, our overall cost is less. That's the effect of reducing that waiting time at $30 per hour by having a 3rd employee. Which, by the way, a lot of managers go, no, we don't have in the budget to hire a 3rd employee. But you show them how much money the company really saves. When we go back to this one, $112 per hour, and adding an employee pays for itself because you eliminate a whole bunch of waiting costs, and that's how you then get approval to get this budget for the 3rd employee hired as fast as you can to take calls. Go ahead.
Is the L sub Q the waiting time?
It's the average number waiting. And L sub Q and L represent the exact same thing in all 4 of these, but the formulas are different. And that's why you got to make sure and use the right formula. L sub Q is always the average number waiting. L is the average number in the system. So it's the waiting plus the average number in the system. Proportion. Less money to bring on a 3rd employee because we eliminated some of that big portion of that waiting cost. So what's the better decision? Having 3 take the calls when we have twice as many calls coming in. Having 3 provide the service compared to 2. Okay? You ready? That's it. That's multi-channel. Or that would review the economic analysis. Here we go with arbitrary. Well, here we go with constant in there. Constant service. The story is about this mechanical pony at the front of, not even Kmart, it's called J-Mart. Mechanical pony at the front of J-Mart provides a 2-minute ride for 50 cents. Now, if I were giving this on a quiz, I might add the word, gives exactly a 2-minute ride for 50 cents. What I'm trying to emphasize is that it will be 2 minutes for anybody who puts 50 cents in it, period. It does not stray from 2 minutes. That's how you recognize constant service. And there's no human involved giving this service. That's usually a kind of a hint that it will be constant. Children wanting to ride the pony arrive accompanied by their parents at a Poisson distribution of 15 per hour. And this could have been, every 4 minutes. They arrive about every 4 minutes. You would then say, oh, I'm being told how much time, I need to convert that to a rate. So 60 minutes in an hour divided by 4 minutes would be 15 per hour. Remember, I'm trying to get you prepared how to recognize if you're being given the time and you need to convert it to a rate compared to being given the rate. Every one of these problems, if you're given the time, you've got to convert it to rate to plug into the formula, so they won't work. Every one of them. And sometimes the arrival's in time or rate, and sometimes the service is in time or rate. So be prepared to convert either one of them or both, or neither. The arrivals happen to be a rate 15 per hour. But I could have, like I said, I could have easily said every 4 minutes. Where is my service? Oh, every 2 minutes. The service is 2 minutes. That's being given to you in time. 60 minutes divided by 2. If a child jumped off the horse in a second and another child jumped on and it started right back up, 60 minutes divided by 2 minutes would be 30 children could be serviced, ride the horse in an hour. So that's 30 per hour is the service rate. There's an example where it has to be converted. So our numbers are 15 and 30. But this is single channel. I just like putting them up here, 13 and 30. The next question might be, what's the probability there's no kids there to ride the horse at all? The horses can rest. You know, you go, okay, this is constant service. You go to the page that has both arbitrary and constant services. One of those six match up to what I just asked, which was, what's the probability that there's no children to ride the horse? That's called the probability of no units in the system, which is the top one. You calculate that. The question says, what's the average number of children riding the horse in the system? You go and say, okay, this is constant service. You find it. You match up what's being asked. Oh, this is the average number in the system. And you do the math to find that number. If you use Excel, you need to take Excel, what you did, and write down kind of what happened on Excel. And if you don't feel confident you wrote down exactly what's taking place on Excel, then you need to send me the Excel spreadsheet after the quiz, after you got my attention, and let me be right there while you're turning on the internet to send me that. Right? Don't turn on the internet before you get my attention. So, let's see. The question might be, what is the average number of children waiting to ride? That's the second one down of the 6. Average, that would be your L sub Q. Arrivals, 15 squared. 2 times 30 per hour service rate, 30 minus 15, service minus arrival. About a quarter of a child, 0.25 is the average number waiting. Not very much waiting, means it's hardly a waiting time. This horse is providing good service. What's the average time a child waits? Now, there's average time in the system and average time waiting. You got to look at, you go and look at the 6 formulas, and you find the one that says average time waiting, and you find this formula, and you say, oh, it's arrival divided by 2 times the service times service minus arrival. You do all the math on this, you get 0.011667. Be careful. What you just calculated is the portion of the time interval that the arrivals and service are in. So, because that 15 is 15 arrivals per hour, and the 30 is 30 service per hour, that is a portion of an hour. But the question probably is going to say, just to prepare you, what is the average time a child waits for a ride in minutes? Might say in minutes or seconds. So you go, okay, this is the portion of an hour. To convert this maybe to minutes, you multiply that times however many minutes are in an hour. If you want to figure out how many seconds, you multiply this by however many seconds are in an hour. But that's a portion of an hour. So that times 60 should be really close to 1. 1 point something that's really close to 1 probably. 0.01667 times 60. 1.0 something maybe. I don't know. Robin, help me out. What is it? 1 point what? Darn it. You were right on it. Man, way to fool me. Okay. Anyway. Here's arbitrary. There's something in this story that's going to make you realize this is arbitrary. You ready? University Student Center has one self-service copier machine. On an average, 12 customers per hour arrive to make copies. Does it need to be converted, or is it already a rate? Not all at once. I can't hear you. It says it's already in a rate. You ask yourself, did it just tell me how much time or how many in a period of time? That's your question. How much time, or did it just tell me how many in a period of time? If it's telling you how much time, it needs to be converted. If it's telling you how many in a period of time, that's rate already. Don't convert. Students are arriving at 12 customers per hour to the copy machine. That's how many per unit of time, hour, doesn't need converting. It follows a Poisson distribution. For this class, all arrivals are Poisson for these waiting line periods. The time to copy documents follows approximate normal distribution with a mean of 2.5 minutes and a standard deviation of 30 seconds. Something about this just told you it's arbitrary. What was it? You got it. Thank you. The moment you see this, sometimes it might say variance. If it does, all you got to do is square root it and you got the standard deviation. If it's the variance or standard deviation describing the service, right there you should say that's arbitrary. And whatever you're going to be asked next, you know to go to the page for arbitrary and use those formulas. And now we're getting close to what makes this particular one of the four hard. Because standard deviation must be left in time, not rate. And the time has to be in the same unit as whatever you make arrivals and services rates. I know I'm going to lose some people here. I'm going to repeat this. For example, our arrivals are 12 per hour. If we have service per hour, then our standard deviation has to be in hours. Everybody hear that? Some people take the arrivals and convert it to how many per minute. Take the service, how many per minute. The standard deviation then has to be time in minutes. The units have to match. But the weird part is standard deviation is not a rate. It's left in time. Your service has to be a rate. And look at our service. The mean amount of time is 2.5 minutes to provide service. Is that how much or how many? Does it need to be converted or not converted? Answer any one of those four words will work. Does it need to be converted, yes or no? I see yes. I see two yeses. Anybody else feel confident? Matt, you're going for it? Because you asked yourself, is this how many per unit of time, or is this how much time? The mean amount of time is 2.5 minutes. That's how much time. And any time you're being told how much time for either service or arrival, you must convert to rate. Go.
But I thought we don't convert that much.
No. You don't convert if it tells you how many in a certain period of time. If it tells you how much time, you must convert it. Change your notes if you wrote that.
Oh, okay, but the standard deviation has to be done.
No, yeah, I'm talking about service now.
Okay.
The service takes 2.5 minutes. It's given to you on how much time it takes, not how many per unit of time. So that has to be converted, and that's how you recognize it. Because I think there's some people, that may even be struggling on when you convert and when you don't convert it. And if you use 2.5, and I'm asking 3 questions from this, not one of them will be right, because you didn't convert it to a rate. And I hate to see all those points lost. So that's why I want to really emphasize, when do you convert arrivals and service to rate? And the question I ask myself is, did I just read something that's giving me how much time it takes? Or how many in a certain period of time? That's the question I ask myself to get to that point.
Could you just always convert to along with the same anyway? So you maybe don't have to.
What do you mean? How would you convert 12 customers per hour?
Yeah, I know. So I'm saying the other thing with the sentence is like just always goes per hour. Whatever.
Well, I'm going to make sure I'm understanding. I see your point. If you're given, something could be given to you on how much time it takes, you have to convert it, unless it's standard deviation. I see your point. We're kind of saying the same thing. Yeah, I just gotta figure out a way don't always convert, only if it's given to you in how much time. But I think he was about to make the point that what if the rates, one of them's per minute and the other one's per hour? And then even though they're both rates, they're in different types of rates, units of time, one's per hour, one per minute. He wasn't going to that, now I can tell by the look on his face. So I took it in a completely different direction, but you would have to still convert, because you have to have the same units of time.
How would you convert that?
I would either take the ones per hour and switch it to per minute by divided by 60, or I take the ones per minute, multiply it times 60 to get it per hour. So they're either both per hour or both per minute. And one person could use per hours, and another person use per minutes, and get the exact same answer as long as you have arrivals and service in the same units of time. On how many per time units. They have to be the same. If it's arbitrary, then this would have to also be in either hours or minutes. This has to be converted to the same units, but in time, not in rate. This is tough. Listen, I'm just gonna make one up right now and see, make sure we all get this. All right? Okay, I'm jumping past this. We haven't even converted this yet, but arrivals. Let's say arrivals take 6 minutes, and service is 12 per hour. With a standard deviation of 10 minutes. Wow, big standard deviation. Okay, there it is. First of all, of the four, which one are we jumping to on the formulas? Arbitrary, because you saw what? Right away, no hesitation. You guys got to be there. Okay, now let's start with arrival. 6 minutes for every arrival. Does it need to be converted?
Yeah.
Do we want to make it per hour or per minute, or what do we want to do with it? Per hour. So if it takes 6 minutes, and there's 60 minutes in an hour, 60 minutes divided by 6 would be 10 of them. Is that right? So this would convert to 10 per hour. Service. Converted or not converted? Yeah, it's already a rate, and it's per hour, the same thing you have this, so now we don't convert that. Standard deviation, though, here's the tough part. Takes 10 minutes. But this is per hour, and this one's per hour. We have to figure out a way to convert 10 minutes to a certain amount of hours. So 10 minutes is what percent of 60 minutes? Because that's the percent of an hour 10 minutes is. And that's the portion of an hour you got to use as a standard deviation, because you have this in hours. So I would take, what is that? 10 divided by 60, which is 0.11166, 116? 16666? So the standard deviation's got to be converted to 0.166666, or end up with a 7 eventually. When you plug this in and do all those formulas, when the standard deviation's in your L sub Q, and that arbitrary. That's the big formula that you need this for. It's 0.1666. Now, the person next to you didn't go per hour. They said, I'm going to use per minute. And they said, this is 6 minutes. How many would that be in every 1 minute? 1 over per minute. 1 over 6. Give me a decimal on that, somebody. That's going to be 0.1666 again, right? Is that? So this is going to be 0.1666 per minute is the rate, which is the same as 10 per hour, which is the same as every 6 minutes. They all mean the same thing. This is in time, this is in rate per hour, and that's in rate per minute. Now that I made that per minute, I got to have my service per minute. 12 per hour. You got to think about that. How long? Let's convert it to time. 7 minutes and 20 seconds. Is that true? You took 60 divided by 12? 60 divided by 12. How many people would be, how many minutes would each one take? 5 minutes?
You don't multiply it?
I don't know. Let's do it backwards. If every customer takes 5 minutes to provide service, how many customers could we serve in 60 minutes? 60 divided by 5 is how many customers? 12 per hour. 5 minutes now, how many could we serve in 1 minute? 1 over 5 per minute. Because we can only, if it takes 5 minutes for one customer, we can only service 1/5 of a customer in 1 minute. Because it takes a whole 5 minutes to do one customer. So 1/5 of a customer. 1 divided by 5, arrivals, 0.16667. 0.2 is our service. We have to use minutes for standard deviation, and look at this. It was given to us in minutes. No converting in this case for the standard deviation because we went per minute, minutes. Now back to this. This one, our arrivals are per hour. 12 per hour. Our service is 2.5 minutes. And our standard deviation is in seconds. We can convert this any way you want. We can go per minute, per hour, minutes, hours, seconds. Yell something. I guess since arrivals per hour are already 12, let's convert service to per hour. If it takes 2.5 minutes to provide service and there's 60 minutes in an hour, how many could be served every 2.5 minutes? So 60 divided by 2.5 is 60, 17, 18? 24? 24? Where was that? Wow, man. So what did I say? 12, 24, right? So we have 12, 24. 12 arrival, 24 per hour. Our standard deviation, 30 seconds has to be converted to hours. Well, first of all, I know that 30 seconds is a half of a minute. So I can convert to 0.5 minute easily in my mind, because 30 seconds is a half a minute. I don't want it in minutes. If it were in seconds, I'd use the number 30. If it was in minutes, I'd use the number 0.5. But I need this in hours. So I got to take 0.5 divided by 60, and I get 0.2, 0.1, 0.0, I can't. Mike, help me, I see you on it.
0.008.
0.008 hours. There's our standard deviation. And because this is per hour, and that's per hour, we had to put our standard deviation time in hours to calculate this right. Now, as we go on to the next slide, you're going to see we went to minutes. 12 per hour would be how many per minute, so we divide by 60. 1 over 2.5 would be one customer, 2.5 of a customer per minute. Go to the next slide, you can see all this. Where is it? 12 per hour divided, that would be 0.2 customers arriving per minute, because we were given 12 per hour. Service is 2.5 minutes. 1 over that time is how many rate per minute. So if it takes us 2.5 minutes to serve one customer. A minute's less than half a customer. Sure enough, it's 0.4 of a customer. So now our arrivals are 0.2 and 0.4, but our standard deviation's in seconds. We got to convert it to minutes. 30 seconds is the same as a half a minute. Now that's in minutes per minute. Whether we use 1224.008 or we use 0.2, 0.4, and 0.5, you will get the exact same answer. This one's in hours, that one's in minutes, and that's how these work. As long as you have the same interval of time for any of these. That's the key. Same interval of time being used. Minutes, hours, seconds. You have a problem in an example I posted. I posted several examples, and I want to show you that because this is the end. There's arbitrary. We did constant and arbitrary today. Is there anything else in here? Average number of customers waiting. You know the formulas. By the way, where's our LSOQ? Look at there. This is color slide. It makes it hard for you to see this, but can you see this? You guys can see it? Can you see it? Kind of. It's the same as on page, whatever the arbitrary page is, 520, whatever. That is the one that uses the standard deviation, and you're squaring it right there. So it's the arrival square times the standard deviation square. Over here is arrival divided by service squared after you divide them. Then you add those together, and that's your numerator. The reason you're calculating LSOQ, average number weighting, is because you've got to find the average number in the system. And the average number in the system is used to do our economic analysis, total cost. And if you are trying to get total cost, you can stop right here. As soon as you have L, you're going to be given the weighting cost, you're going to be given the cost per channel, the number of channels. This is the only thing you needed to finish the economic analysis was this L. Is this starting to make sense a little bit? Because a lot of students find this chapter hard, harder than some of the others. And I've actually changed this lecture year after year to try to make it easier and easier and easier to understand. But I know the first time you see it, it's kind of hard. All right, blah, blah, talked about had arrivals at, what was it, 12 per hour, I think? I have it right here. 12 per hour, 24 per hour, and we converted standard deviation to .008, right? So tell me which one are we going for here? Now, we talked about this last week. You're only using the top three. Do not even look at these two. The top three. That problem we just did as an example would be the first one, second one, or third one down. Second one, it was arbitrary. That third one down, write yourself a note that deterministic and the word constant are the same thing. So that's your constant one, that third one down. Deterministic and constant, basically the same word. Here's the source. So the first one is exponential, whether it's single channel or multiple channel, you're using that first one. Second one's arbitrary, third one is constant, and you don't use the bottom two. We're going to arbitrary. Arrival rate that we're using per hour was 12, is that right? Someone help, is it 12? Okay, and what was the service rate? 24. And standard deviation, now look at what it says. In units of time period, meaning the time period you used above. 12 per hour, 24 per hour, standard deviation in time, in the same units you use. So that's why we converted 30 seconds to .008. 0.008. If anybody has a PowerPoint, oh, wait. Let's pretend we also are been told that, what is it? I'm going to this one. Cost per channel. Cost of, this should say cost per time period for using the system. Really, it should say cost weighting. Cost weighting, let's say, I know that other problem said $30 per hour. 50 cents a minute is what it said. We converted it per hour. And then the cost per channel, let's pretend it's $20, just so we can see how this comes out. Sure enough, the probability of no use in the system, 50% chance. So that means the probabilities that a arriving unit has to wait is 50%. Now, only single channel, and I make that assumption that the probability of a unit having to wait and the probability of none in the system are the exact opposite of each other. Only single channel is that true. Multi-channel, there's no relation. So it's only single channel that I knew that. The average number of units waiting, 0.2592. The average number of units in the system, 0.7592. Now let me go back to the PowerPoint. Was that 0.7592? Where is that? 0.7592. Right there. Now don't forget that number, because watch what I'm going to do now. I'm switching everything to per minute. It was 0.2 or 0.25. Anybody got the PowerPoint? On that next slide, it said 0.2 or 0.25 maybe. 0.4. You gotta find it. 0.2. There it is on slide 51. So per minute would be 0.2. Service then was 0.4, I think. Is that sound right? And then the standard deviation now has to be in minutes. It was 30 seconds, so in minutes that'd be a half a minute, 0.5. Still, it's, cost per time period. It's not $30 a minute, it's $30 an hour. How much is that in a minute? 50 cents, right? And instead of $20 an hour, I've got to take 60 divided by 20 divided by 60. What is the cost per minute? Point what? Point what? Did you have it? That was you? What is it?
It's 20 divided by 60 is 0.32.
Okay, so 33 cents. You ready? 33 cents a minute. Does that make sense? Is that right? What's 33 times 60? 33 times 60, what do you get? You get 30? No, I mean, what was it? 20. 20.
Yeah.
Was that our weight cup? All right. Our cost per channel? It was. You ready? So we have our economic analysis per minute, arrival per minute, service per minute, and our standard deviation in minutes. What was our L before? It was 0.76. Average number of units in the system, 0.76. Is that what it was? You can go back here. It was 0.76. There it is. So as long as you have these numbers, you can have completely different numbers than someone else doing the same problem, but as long as they're all consecutively in the same units of time, minutes, seconds, hours, whatever it may be, as long as they're all the same, you'll get the right answer using different numbers. examples. I put these up for study tools. This one, let's look at this one. It says, manufacturer company operates equipment repair. Okay, here we go. This isn't per hour, this isn't per minute, this isn't per day, this isn't per second. This is per shift, 8-hour shift. It's a little different. It says, the manufacturer company operates equipment repair business where emergency jobs arrive randomly at a rate of 2 jobs per 8-hour day. Didn't tell you how much time it takes for them to arrive between arrivals, but instead it's telling you how many per unit of time. The unit of time is what's weird. It's in 8 hours. So it's 2.2 per 8 hours. There's the rate. Next, says the company's repair facility is a single service system, single channel, operating a repair technician. The service time varies with a mean repair time of 1.6 hours. Does this need to be converted or is it rate? The mean time it takes to do a repair is 1.6 hours. Does that need to be converted or is there already a rate? It needs to be converted. It's given to you on how much time it takes. But be careful. Your instincts are going to say, I need to convert 1.6 hours to how many per hour. And it all depends what you put arrival. If you leave the arrival at 2 per 8 hours, you need to convert service to how many per 8 hours. And then the next sentence says, the company's, whoops, I passed it. The mean repair time is 1.6 hours and a standard deviation of 1.25 hours. So, if you change arrivals, if you leave it at 2 per 8 hours, and then service gets converted to how many per 8 hours, that standard deviation needs to be the amount of 8 hours. And it's the amount of an hour. If you convert arrivals to the how many per hour, service to how many per hour, standard deviation does not change. It's already given to you now. Everybody get that? That's a tough one because the arrivals being given in an 8-hour shift throws a loop in anything you've seen so far. That 8-hour shift is the unit of time. That's what makes it so weird. To make it easier, I think I'm going to, I don't know what I did down here. I can tell what I did. I switched it to per hour to make it easy. So I said if there's 2 every 8 hours, that means there's a quarter of a customer every hour. So a quarter of a customer times 8 hours every 4 hours, there'd be a customer. Quarter, 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 here comes a customer. Quarter, 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 there's the second customer. 2 per 8 hours. So 0.25 per hour. Service, 1.6 hours. So per hour would be 1 over 1.6. Be, 5/8 of a customer per hour. Because we already could go, it already takes us longer than an hour just to service one customer. 1.6 hours. So we can't even do a full customer. But now we have this at a rate per hour. We have service at a rate per hour. Standard deviation can now be used in hours. So there's no converting it, 1.25. This goes on. See. There, right there. This probably is asking you to do an economic analysis, total cost, right there. So to get to total cost, I had to get my arrival rate, service rate, calculate my L sub Q, so I could get L, so I could plug it in. Also, there must be a waiting cost up there in the story. There's probably a cost per channel in the story. And sure enough, I'll go back up. It says the company's cost of repair operation is $32 per hour. So there's our cost. It's a one-channel operation at $32 an hour. In the economic analysis, the waiting line system, the company uses $45 per hour cost for customers waiting during the repair process. So our waiting cost is the 45, which is right there, cost of waiting times L we got to calculate. And our cost per channel is 32 times the number of channels, which is a single channel operation, 1. All the hard parts right there on that L, especially because this is arbitrary, so that L sub Q is not the short formula, it's a little bit longer with that standard deviation. Arrival squared, standard deviation squared, multiply it. Arrival over a service, square it. Add it to the previous calculation, there's your numerator. I gotta remember this. 2 times 1 minus arrival divided by service. Get that ratio, subtract 1, then multiply times 2. There's your denominator, 1.2. Divide that into the numerator. Our L sub Q is 0.2147. To get our L, we take that 0.2147, we add the arrivals, 0.25, divided by the service, 0.625. Add that to there, we'll have our L, plug it in there. Our total cost, all the answers here for you. L is taking that L sub Q, add it to the 0.25 right there. 45 is our waiting cost, times 0.614 is our average number in the system, L. $32 per channel is the one channel system. Our total cost per unit of time, which is per hour, $59.66. Everybody see? You know what to expect on the quiz. Print this off. You got it. Let's do another one. Here's a multi-channel. Here's a multi-channel. And we talked about, I think I showed you this one last week, but let's talk about it again real quick. You're trying to decide between 2 or 3 channels of service. The arrival rate equals 2.5 customers per hour. The mean service time per channel is 10 minutes. The waiting cost equals $25 per hour, and the cost per channel is $60 per hour. There's all the information you need, but there's something that has to be converted. What has to be converted? There's really a class here, I swear. What has to be converted? You've got to be kidding me, you guys. You're scaring me. Now the quiz is on Thursday.
Service time.
Service time. It's given to you in time. You've got to convert that. What did it say? 2.5 minutes? 10 minutes. How many customers in an hour, because everything else is per hour, could be served? 6. 60 minutes divided by 10 minutes each of them is 6 customers. So now we have arrival at 2.5, service at 6. Is that right? There it is. And this is multi-channel, so we're not going to calculate that piece of O if we have to do an economic analysis. We're going to look on that table. And we get the ratio of arrival divided by service rate. We go to 0.4166, or as close as we can get to it on that table. This is, we're trying to decide between 2 and 3 channels. So we'll grab the 2-channel number while we're there. We'll grab the 3-channel number so we can get them both done at the same time. Once we have those 2 numbers, where's 2-channel here? 2-channel, you'll find it right around 0.65. 3 channels, a little larger, 0.665. Got it, darn close to each other, though. Now that we have our probability of no units in the system off the table because it was multi-channel, we can calculate our L sub Q. I forgot, what is this? Is that our arrival ratio? There it is. Arrivals divided by service squared. Our arrival times our service. Multiply those. 2 is the number of channels minus 1. Factorial, which is 1 factorial is 1. 2 times the service rate minus the arrival rate. Then square it. You end up getting, here's our answer here, 0.01875. Use the software, 0.0189. Darn close to each other. Plug that in to get your L. Add to it arrival rate divided by service rate. There it is right there. Add those, you got your L. Now to get your economic analysis for 2-channel. Jump down here. I don't even need to see it. Take your cost per channel, which is $16 times 2 channels. There's $32. Take your waiting cost of 25 times the L for 2 channels. You just calculate it right there. Then add it together. Now do the same thing for 3-channel. 3-channel, we already looked it up right up here. And now we're taking, wait a minute. Oh, L. We're doing the same thing, but we're replacing, where is this? Right here. We're replacing this with 0.665. Everything else is the same. Nothing else changes for 3-channel except for that right there. We're getting darn close to the same number probably. We do all the math. What was 2 channels L? The average number of the system was 0.01875. If you did it for 3-channel, that one little change. Oh, I forgot there was one more change. Right here. This is, whoops. This would be 3 minus 1 factorial. There's the big change. I forgot about that one. Because there's 3 channels now instead of 2. So 3 minus 1 is 2. 2 factorials, 2 times 1 is 2. So that's what makes this so different. Now that we have that, we take that times the waiting cost of $25. 3 channels times $16. We compare if waiting cost has been reduced enough to go with 3 channels instead of 2. Are you recommending 2 or 3? 2. The cost is lower. We went $42.89 where that extra channel. The cost of adding a third person or third whatever to provide service does not outweigh the reduction in waiting costs, and therefore ends up costing more money. See how the reduction is not enough? Our L went from 0.4356 to only 0.4182, which means that our $25 got reduced, but not by as much as $16 increase in cost per channel. So that's where that comes in. We also compare these two numbers to the probability of a customer having to wait, because we're customer-oriented type of business, even though we're not the Secretary of State, right? And by the way, I was there today, and it only took them 50 minutes. And I was happy about it. That's how much we've been psychologically, to be happy about only having to be the Secretary of State 50 minutes. Because we expect it to take forever. Our expectations, as long as it's under our expectations, marketing majors. All right, so you would recommend 2 channels based on cost alone. If you're not worried about the probability of the customer having to leave. All right, so there's another example. One more. Let's do, this one is, you got to go to number 10 in the back of the chapter here. I'll read it to you. I'll put it up here. Number 10 says, hey, this tire company, I can't even see it. This tire company is hiring a new mechanic to handle all tire changes for the customer ordering new set of tires. 2 mechanics applied for this one job. One mechanic has limited experience, and we would only have to pay $14 an hour. The service rate average, or the services at an average of 3 customers per hour. Has to be converted or not converted for this employee's service? No, because it's already given as a rate. It's how many per unit at a time, not how much time. So this does not have to be converted. It says this employee can provide 3 customers per hour. The other mechanic, who has several years of experience, can be serviced 4 customers per hour, faster. It does not have to be converted. There's a rate, 4 customers per hour, but the pay would be $20 instead of $14. So the pay per channel changes in this case. What's the waiting cost? Assume that the customers arrive as the company's garage at the rate of 2 customers per hour. Arrival doesn't change no matter which person's doing the job. 2 customers per hour. And where's the waiting cost? If the company assigns a customer waiting cost of $30 per hour, which mechanic provides the lower overall total operating costs? So hiring the more experienced one will cost us more, but does the faster service reduce the waiting cost enough to cover the additional cost per hour? What's the additional cost? 14 versus 20, $6 per hour. Our waiting cost would have to come down by more than $6 for us to get authorization to hire the more expensive employee. And so then we go here and we go, oh look, all the numbers, 6 numbers that we would have to calculate, or 3 of the 6, are given to us, 2 of the 6. Wait, before I do that, which of the 4 is this waiting line theory? Which of our 4 choices? Which service is it? What kind of service is it? Is it, what are the names? Arbitrary? Is it arbitrary? No, because? That's right, no standard deviation. So we got 3 more now. Is it constant? Because there's a human involved, and we were already told one human takes a certain amount of time and another one takes a different amount of time. So we got 2 left. Which one is it? Single or multiple channel exponential are the other 2 choices. She's saying single. Anybody agree with Peggy? Anybody disagree with Peggy? Not you, Peggy. Does Paige agree with Peggy? Okay. Anyone else? Jim, you agree with Peggy? He's still thinking about it. Matt? Not sure. You do agree? A lot of students think this is multiple. but the two of them are not gonna be hired at the same time to work. If both of them were hired to work, that would be multiple. Only one gets the job, and only one's doing it at a time. You gotta look at these as two separate, single channels. And if they were multiple channel, we wouldn't have two different costs per channel to have the employees. You'd probably only be given one number. We have two different costs per channel because only one's gonna do it or the other. So you gotta calculate using the single channel exponential, the L, unless it's given to you. Sure enough, it is given to you. Now, my question is, hang on, quit looking. Hang on, how do I get this where you can't see? And then stop. Okay. Well, that's all. You can't see it. Okay. We want to do the arrivals are at 2 per hour. This person can service 3 per hour. This is our lesser expensive employee. We'll take his or her hourly wage, which was, I can't remember the amount, was $6 less than the other person. 14 times 1, because only one channel is doing it at a time. Then we'll take the waiting cost, which was how much? Now you're all over that. The waiting cost, 20 maybe, or 25, what are they? They use some number. It says, remember that problem? Oh, it's in the book. It's $30 per hour. Times what is my question? 14, is that what you said the cost was? Times 1, 30 times what? 2. Times 2, that's right. Now, what if you weren't given these letters? Is that what you look for, by the way?
Yeah.
What if you weren't given the letters? How would you figure out which one to use? Well, yeah, you've got to look up what L is. You've got to remember L is economic analysis. No matter which of these 4 you're using, it's L, L, L. And L is always the average number in the system. Now, there's different ways to calculate it if it's not given to you. That's why you got to know which problem you're doing. But L represents the same thing in every one of those formulas. There's just different formulas. That's what you got to find, and you probably won't be given the letters. So know that for economic analysis, average number in the system is the number you use times that waiting cost. We would use a 2 when we're analyzing 3 channels, or the employee, that can handle the service 3 per hour. And then we would use the number 1, that's L, for the employee that can handle 4 customers per hour. So now let me get back to the answer. One employee is going to use $14 times 1, and then it's L. The other employee is using $20 times 1, and it's L. The L is so much different by this more experienced employee being able to help that many more customers provide service that it brings our costs significantly down in the waiting cost compared to the increase of only $6 in pay. So, hey, whoever's handling the budget, I want to hire the more expensive person, even though it's $6 more an hour. Because in the big picture, it's saving us $24 an hour in waiting costs because this particular person is that much faster. And we have them coming in at 2 per hour, and he can handle 4 per hour compared to the other one 3, brings that waiting cost down, and we should be willing to pay the extra money for it. Don't get me wrong, I'm so cheap, like I said before, I don't know if we discussed that one, that I would hire the 14 and train them to be as fast as this person. That's how cheap I am. Even if I have to train them myself. Because I always said when I was in the business world, that any job, any employee that I have can do, I can do it. I always said, I'm not going to allow an employee to ever be able to say, but you can't do my job. So I made sure to learn every job. And that way, I can figure out ways to make the job better, make it faster, make it easier, and I would train a new employee if it were needed to make sure they're doing it right. This is it. You're having a quiz, I think tomorrow. Does anybody want to take it tomorrow? Because you can. There's like 1 or 2 empty seats still in the other class. No? All right. I will see you then on Monday after Thanksgiving, a whole week from now. Oh, wait, I got to answer that. Shoot.
I was going to say,